Okay, so hello everybody. Welcome to the last session of Wednesday's workshop session. And today we're very happy to have Atish Dabholkar from ICTP, the director, who is going to talk to us about 3 avatars of mock modularity. Atish, please.
Okay, thank you very much, Abhiram. So the elevator pitch is that modular symmetry has always been very important in physics, both for dualities or for holography from many different perspectives. But mock modularity, surprisingly, is coming to become quite important. And I think it's going to be a feature that it will slowly get more and more into the physics literature. And I think from a physical point of view, we now understand it has something to do with non-compact path integrals and boundaries of field space, which is where mock modularity. So I think we both understand now how mock modularity appears in physics and what is the physical explanation of that mock modularity. So the take-home message is that mock modularity is related to non-compactness of path integral or of the manifold and things like that. Okay, so I hope I can give you some sense of this. I think my talk, I had given a similar talk a few months ago. Of course, when you are giving a talk online, it's hard to tell. You know, when I was giving a talk in California, there were people from New Jersey and from Chicago and from Cambridge. So likewise here, so some of you may have heard this part of this talk, yeah, all parts of this talk. So I apologize to them, but I will address it to people who have not heard it at all, because I think it's a very interesting but complicated story, and I want to go slowly, so that you at least go away with a picture of how mock modularity fits in physics. So these are the 3 avatars of mock modularity. This is the famous 3-headed DT in India. And the 3 avatars have to do with holography, topology, and duality. And this is starting with my work with Murthy and Zagier. I mean, this is how I got into this story. Sorry, what am I doing? I would like to be able to, okay. Yeah, so Murthy and Zagier, these are my, and then subsequent work and more recent work. So these are my collaborators. Samir is at King's College. Don Zagier is actually now spends time at ICTP. Diksha was my student at ICTP. Pavel Putrov is a faculty at ICTP. Arnab was a postdoc at ICTP, and now he's a faculty in India. And Francesca is a current postdoc, and Witten. So let's start with the mock theta functions. In Ramanujan's famous last letter to Hardy in 1920, he gave 17 examples without giving any definition of what he called the mock theta functions. So they're mock because they are like theta functions, but they are not quite like theta functions, with hints of modularity. And a typical example is this function, which looks kind of like a hypergeometric function. And for any sort of a mortal being, this doesn't seem to have any modularity, but Ramanujan, being Ramanujan, noticed that this has some very interesting modularity properties. And despite much work by many eminent mathematicians over the past 100 years, this fascinating mock or hidden modular symmetry sort of remained mysterious for almost a century, until the thesis work of Zwegers in 2002. And the basic understanding of mock theta function now is that it's almost modular. And because it is almost modular, it is difficult to characterize it. It's a bit like trying to characterize a figure which is almost circular. You know, circular figure you can characterize very easily, but if you say almost circular, you have to tell me whether there is a wiggle going to the left, to the right, or how it is. Is it ellipsoidal? In what sense it is not circular? And that's why it remained very mysterious. So before going into mock modularity, let me just very briefly remind you of modularity, because I guess not everybody in this generation of physicists, string theorists who start with holography may be trained in worldsheet methods. So modular form, and we will use these definitions later. So a modular form of weight k is a holomorphic function on the upper half plane, which basically is invariant under this big large group of modular symmetries, SL2Z symmetries. So if you take this scale factor, I mean this form factor, C tau plus D to the power minus k, and you can see the function is essentially invariant, where A, B, C, D, and k are integers, and AD minus BC is 1. This is the SL2Z group of matrices. In particular, it is a translational invariant. So you can do its Q expansion in terms of exponential of 2 pi I to Fourier expansion. And the Q coefficients AN contain all the information about this function. And modularity has already appeared in physics in 3 important contexts, and it's the same context in which mock modularity will appear. One is holography. If you consider ADS3 quantum gravity, so ADS3, Euclidean ADS3, if I remind you, is basically a solid cylinder. And these 2 sides are identified. So basically the conformal boundary of a solid cylinder is a T2. And the diffeomorphism, global diffeomorphisms acting on this conformal boundary up to a scaling are essentially the SL2Z symmetries. So the global boundary diffeomorphisms is where the SL2Z symmetry appears in holography in the ADS3 context. Then in the context of 4-dimensional quantum gauge theories, it appears the congruent subgroup of SL2Z is typically the S-duality group. The famous example being the n equal to 4 super Yang-Mills theory, where the S-duality group is actually SL2Z itself. And then in topology, for a 2-dimensional conformal field theory, SL2Z is the mapping class group. So if you're computing, say, the partition function of some conformal field theory on a torus, on a 2 torus, the Riemann surface, then its mapping class group is again SL2Z. And therefore, physical observables in all these 3 physical contexts, we expect them to exhibit modular behavior, because these are important symmetries of the theory. And in the case of holography, it's really a global diffeomorphism. It's a gate symmetry. So you better not violate it. And now, not only is modular symmetry important, but it is very powerful. And the power of modularity basically comes from the fact that these are highly symmetric functions. So very important theorem is that the ring of modular forms, it's a ring because you can take one modular form F and you can always multiply it by another modular form, F tau and G tau. And if this has weight K and this has weight K prime, you'll get something which has weight K plus K prime. You will again get a modular object. So basically you generate modular objects by multiplying them. So it's a ring. And this ring is generated by just 2 Eisenstein series. So for example, if you want a weight 12 modular form, there are only 2 possibilities, E4 cube and E6 square. And you just have to figure out what are the coefficients A and B, because it has to be a linear combination of these 2. And therefore, on the right-hand side, you have infinite number of Fourier coefficients, the Q coefficients. But if you know secretly that a priori it has infinite number of Fourier coefficients, if you just use the tau going to tau plus 1 symmetry. But because of the SL2Z symmetry, actually you just need to know 2 coefficients. So if you know the first 2 Fourier coefficients of this function, then they have determined the function completely. And this is some trick that I learned from Don Zagier, who's a bit like Ramanujan in the way he works. And this is actually somehow the power behind some of the magic that Ramanujan had, that if you know secretly that some function has modular properties, then you can write sort of magical identities saying that the left-hand side is equal to right-hand side just by checking the first few Fourier coefficients, and then you are done. So just the first few Fourier coefficients determine the modular form completely. So that's the one very powerful fact about it. The second powerful fact about it is that the modular symmetry relates F tau going to F minus 1 upon tau. And if you think about in the context of conformal field theory, it relates high temperature to low temperature, or strong, in the case of gauge theory, strong coupling to weak coupling. And therefore, it gives you a huge amount of information from a physical point of view, that by you can relate strong coupling computations to weak coupling computations, or high temperature computations to low temperature computations. And the famous example of that is the Cardy formula. But in fact, there is a very beautiful generalization of that, which is known as the Hardy-Ramanujan-Rademacher expansion, which gives you an exact expansion of AN in terms of Bessel functions. Not only asymptotically, but it's an exact convergent expansion. And this fact actually became important in the exploration of quantum entropy of black holes. And some of you might have seen, I had given some lectures in the school at Princeton, that the Cardy formula is roughly like exponential of the Bekenstein-Hawking entropy for the black hole context. And if you want to compute the exact quantum corrections to the Bekenstein-Hawking formula, then what you are required to do on the counting side is to really look at the Hardy-Ramanujan formula. And in some simple cases, you can actually reproduce this entire Hardy-Ramanujan expansion from doing a path integral. So it's a very beautiful connection between something that is purely complex analytic, like a path integral, which gives rise to something which is purely number theoretic, which is the Fourier coefficient of some modular form. So therefore, modularity has been very powerful. So by the way, I have how many 45 minutes you said, right?
You have up to an hour, so you have like about 50 minutes more, 55 minutes.
50 minutes, okay. So I won't rush it, but I will also try to keep an eye on the time.
Sure.
So so now let's come to the mock modular form. What is a mock modular form? Okay, there is a slightly more complicated story, but in the simplest context, the definition of a mock modular form involves actually a pair of functions, not just one function. It's a pair of function f and g, where f of tau is a holomorphic function of h, like the function that we have been thinking about, the ordinary modular form, with some growth properties at tau, let's say imaginary tau going to infinity. And g tau is a holomorphic modular form of the kind that we discussed, of weight 2 minus k, such that f of tau a priori does not have any nice modular properties. However, the sum f hat tau and tau bar, I mean, I explicitly show tau bar, it depends both on tau and tau bar, is the sum of f tau and g star of tau tau bar. I will tell you what is g star. G star is going to be a function that is constructed out of g, but that function is not holomorphic, such that this whole object together transforms like a holomorphic modular form of half integer weight k of some congruent subgroup of SL to Z. And so this was the definition given by Zwegers and Zagier. Zwegers was a student of Zagier when he did this doctoral work. And in this definition, f is called the mock modular form. So that's the function that I showed you. It's the mock modular form of the kind, the mock theta function that Ramanujan wrote down. It is holomorphic, but it is not modular. G is called its shadow of that mock modular form. It is both holomorphic and modular, but it is just a shadow. It doesn't know about the actual mock modular form. And f hat is called the modular completion because it is modular. However, as we see above, it is not holomorphic. So the essence of mock modularity is this some kind of an exclusive OR property, that is holomorphic XOR modular. The function f is holomorphic but not modular, whereas f hat is modular but not holomorphic. And this incompatibility between holomorphy and modularity, that's the essence of mock modularity. And of course, Ramanujan never specified what is this function g. So for ordinary mortals, there was no way to verify whether this function f, whether in what sense does f have modular properties. And as we have seen, f actually does not have modular properties by itself. But you can add to it a small correction term in such a way, it is possible to add to it a small correction term in such a way that the resulting function has this full SL to Z modular symmetry. And as we have seen, this is a very large group of transformations, so it gives you a lot of control over the properties of that function. Another way to characterize it, which is closer to the physics application, is to think of it as a holomorphic anomaly, that a modular completion of a Mach modular form is related to the shadow by a holomorphic anomaly equation, which is here. So basically, if you take the tau bar derivative of f hat, you don't get a 0. And you fail to get a 0 by a function which is itself a complex conjugate of a modular form. So g of tau was a modular form, you remember, and this is the complex conjugation of that modular form. So the shadow is both holomorphic and modular, but it does not determine the modular completion. The non-holomorphic correction g star of tau by itself, it is not modular. However, when you add it to this Mach modular function, this that Ramanujan was talking about, which by itself is not modular also, the completion contains all the information. So completion is really the object that contains all the information, but it is not holomorphic. So some of the nice theorems that I referred to, they do not apply to this non-holomorphic modular objects. However, you recover modular symmetry. And now let me tell you how to construct this G star. The G star is constructed using in terms of the Fourier coefficients of this function G tau. So if suppose the G tau has a Q expansion Bn Q to the power n, then G star is constructed as follows. In terms of an incomplete gamma function, it is some complicated formula, but main thing to focus on is you have Bn bar, you take the complex conjugate of this Bn's, and you multiply that by a gamma function and take Q to the power minus n. And it might look to you that this will diverge and so on, but somehow the gamma functions are such, their asymptotic properties are such that this is, you get a nice convergent series. And let me recall you that the incomplete gamma function is basically defined by in this manner. It's related, for example, basically it's the gamma function of Euler, but you instead of starting at 0, you start at x. So the incomplete gamma function that will actually make its appearance again. And that's how the physics derivation will go. Somehow the incomplete gamma function will appear when we talk about some non-compact Witten index or non-compact elliptic genus. And that is how we will make contact with the path integrals that lead to this Mach modular forms. So just to summarize, I think it's a good geometric analogy. I was asked in one of these popular things, how to explain Mach modular form, and I think this is a good geometric analogy. That a holomorphic and modular function is a bit like a blue circular figure. Now, circular figure has a lot of symmetry. It's rotationally invariant under the U1 symmetry. Similarly, a modular form is highly symmetric. It's invariant under the SL2Z. And holomorphy is like the property of being blue. And Mach modular form is sort of the completion of a Mach modular form, if you want to think about it, is like this figure where part of it is actually red. Part of it is red here. And by adding that little red piece, you render the whole figure circular, but it's no longer blue. The blue part by itself, which is the Mach modular form. So you can think of this as the f function, f tau. The whole figure is like f hat of tau. And this little circular segment, you can construct out of this some another little blue circle, which is like g of tau. So I think it's a pretty good geometric analogy that f of tau, f hat of tau is like this figure which is not blue but is circular. F of tau is this figure which is blue but not circular, and g of tau is both circular and blue. Now there is a simple generalization of modular forms which is called Jacobi forms, and some of you are familiar with it and some of you may not have seen this. And it's basically you add one more degree of freedom or one more variable. So it's a function of two variables, tau and z, defined on the upper half plane times complex plane. And such a function is called a Jacobi form of weight k and index m if it is modular in tau and elliptic in z. And roughly speaking, what we want to is that it's again very symmetric under this modular group. Tau goes to a tau plus b c tau plus d, and z also transforms. Then it's essentially up to this factor and phase, it is invariant. And sorry, let me erase this. And it is also invariant under it's doubly periodic effectively up to a phase. So you can think of this, the tau parameter, you can think of it as a torus, the tau parameter of a two-dimensional torus, and z you can think of as the coordinate on the torus. So roughly speaking, and you can get the torus by doing some kind of a lattice, modding out by a lattice, the upper half plane. So roughly speaking, the Jacobi form is a function which you can sort of extend, not quite because of the phase, but it's essentially doubly periodic up to a phase in the entire complex plane. And so it is sort of invariant up to phases and some factors under the Jacobi group. Jacobi group is basically the group composed of the modular group and the translations in the lattice translation in the Z plane. So in the Z plane, these are the lattice translations. And once again, it admits a Fourier expansion. And now the Fourier coefficient will depend on two integers, C, N, and R, Q to the N, Y to the R, where Y is like e to the 2 pi I Z. In the same way, Q was e to the 2 pi I tau. And it appears in quantum field theory and in topology in the context of elliptic genera, because you can define, if you take a conformally invariant nonlinear sigma model with target space X, let's say, with 2, 2 superconformal symmetry, then 2, 2 superconformal symmetry means that you have, on the left, you have a Virasoro algebra generated by Tz, but you also have a current J of Z. And similarly for the right movers. And so you have L0 and J0, which are the zero modes of this Tz and Jz. So, okay, I have called it J left maybe here. And actually, I have called it F right, in fact. So let me erase this. So F right is like the zero mode of Jz, and much like the L0 is the zero mode of the stress tensor. And then you can construct a partition function of this kind, an index partition function, because fermions are both on the left and the right are odd under this F right. This is like the fermion number. That's why I've called it F right rather than J. So this theory has bosons and fermions both on the right and the left. And what you're doing is that instead of computing a normal trace, which would have been q to the power h left, q bar to the power h right, you are computing an index trace -1 to the f right plus f left with this insertion of operator. And this is, you can think of Z as like the chemical potential for the charge. From the two-dimensional conformal field theory point of view, it's like the chemical potential for the charge f right. In much the same way, the tau is the chemical potential for the left-moving Hamiltonian, which is L0 or H right, H left, and tau bar is for H right. Sorry, okay, here I also call this equal to H right. Sorry, I'm mixing left and right, okay, but you understand what I'm saying. Now, such a partition, you can represent this by a path integral. If you have a, so a good example to keep in mind is that you suppose you have a two-dimensional sigma model, conformal sigma model with K3 as the target space. If you have K3 as the target space, then you can define its elliptic genus in this manner. And by conformal symmetry, the path integral is modular. And by, there is a spectral flow symmetry, which is sort of, if you bosonize this charge, then translations of this compact boson give you a spectral flow symmetry. You can argue that the path integral has to be elliptic. And therefore, this function has the properties of a Jacobi form. And since elliptic genus is a very important object in understanding the topology of manifolds like K3 and so on, elliptic genera naturally occur in the context of topology. You can also think of it from a physics point of view as a right moving Witten index that counts the right moving ground states, because if you look at this, only the left movers are excited. Sorry, left movers have a chemical potential. So it means that the right movers have to be all in the ground states, because of the fermionic symmetry, anything which has non-zero right moving energy, they come always paired as bosons and fermions. So effectively, all the heavy degrees of freedom from the right moving theory cancel out in pairs, and you're only left with the right moving ground state. Okay, so it's a little bit like the right moving Euler character or something like that. Okay. There are two examples of the Jacobi forms which are quite important. One is the elliptic genus of K3, which should have weight 0 and index 1. And this you can compute, and it is given by this function. It is basically given in terms of the Jacobi theta functions. If you recall, theta 2, theta 3, theta 4 are the even theta functions, meaning they are even under z going to minus z. And because of that, it doesn't vanish at z equal to 0. So you can take these three ratios and multiply by 8. And it's easy to see that when you put z is equal to 0, you will get the Euler character goes over to the Euler character of K3, which is 24. It will be 8 times 1 plus 1 plus 1. So that's 24. And this is not a coincidence, of course, because the elliptic genus contains a lot more information than just the Euler character. It's just some topological generalization of an Euler character. And similarly, you can define a modified elliptic genus for a T4. Because it is modified, it turns out the weight is actually -2, because you have to insert some fermionic currents to soak up the zero modes. As a result, the index, instead of being 0, is -2. And again, you can see that it's very explicit, because T4, we have basically 4 bosons and 4 fermions. So it's this function, the fermions are charged divided by, so this is a fermions divided by bosons, that's the partition function. And up to some factors of Q and some signs and something coming from the zero mode. So if you put it all together, you get exactly this, theta 1 square divided by eta to the 6. And because there is a, from the zero modes, there is a sine pi z factor coming in. So as z goes to 0, this has a 0. In fact, it has a double 0. Now, once again, Jacobi forms also have a very nice theorem. A ring of Jacobi form is finitely generated by these two functions. So these two functions are very natural from the physics point of view, but also from a mathematical point of view, they are very natural. They generate A and B completely the ring of Jacobi forms. So for example, if you want a Jacobi form of weight 4 and index 2, but this time the coefficients of the ring can be themselves modular forms of the single variable, tau variable. So just to illustrate this theorem by example, so this is Eichler and Zagier. Suppose you want weight 4 index 2. If you look at our objects, these are the only two objects. This has index 1 and this has index 1. So the only possibility we have to get index 2 just by adding index is a square, ab, and b square. But a square will have weight -4, and we want weight 4. So you multiply that by e4 square to get weight 4, and multiply by some coefficient. AB will have weight -2, so you multiply by e6 to get weight 4. And b square will have weight 0, so you multiply by e4. And that's it. This is the only possibility you have. So once again, instead of determining this C and R, which are their Fourier coefficients in a big lattice of infinite number of Fourier coefficients, you just determine these 3 coefficients if you know the weight and the index of this object. So once you know some properties of this object from some physical consideration, without really more or less lifting your finger, you can do the calculation. For example, for the elliptic genus of K3, you can quite easily argue that 8 is you just determine this 8, and then this is the only function which has the required properties. Now, one important property of Jacobi forms is that they are equivalent to vector valued modular forms.
This question.
Yes.
Here we say ring of Jacobi forms. Do you mean ring of weak Jacobi forms?
Sorry, ring of weak Jacobi forms. Yeah, I have been a bit sloppy. There are some growth conditions that we have to worry about, and you can say that it's either it grows so fast or not so fast. So this can be weak Jacobi form, it can be holomorphic Jacobi form, and depending on the growth condition. So thank you, actually, that's an important comment. So you get what is known as the theta decomposition, basically because Jacobi form is essentially translational invariant up to phases. So you can take care of those phases, and there is a simplest kind of translational invariant function that you can write down with the right phase properties, and that's the standard level m theta function. So you just take q to the power something, it's basically Gaussians, and multiplied by the phases such that it has the right transformation properties of the Jacobi form. And therefore, essentially the Jacobi, the double periodicity you can take out of the picture. The Z dependence you can completely remove from the consideration. And you can express this function phi tau of Z in terms of this very explicit and well-known functions, standard level m theta functions. And then the only non-trivial information is contained in this vector HL of tau, which now depends only on one variable. So therefore, a Jacobi form phi tau of Z of weight k and index m is equivalent to a vector valued modular form HL of tau of weight k minus half. K minus half because this theta function has weight minus plus half. So just to add up the weights, if you want to know object of weight k, HL have to be of weight k minus half. And so these were the kind of objects that Ramanujan had encountered. So this is all mathematics. Now, how does it come into physics, this mock modular forms? Okay, I have told you that modular forms, of course, appear in physics in a very important way. But what about mock modular forms? And there is a very nice quote, actually. There's a very nice article. I strongly recommend you to read it if you get a chance. You can find it on, it's called a Walk Through Ramanujan's Garden. This was written at the time of 1987 Ramanujan Centenary Conference. And he talks about all the contributions of Ramanujan, especially the ones that he was particularly interested in himself in some counting problems. And then he goes on to comment, my dream is that I will live to see the day when our young physicists, and actually I was a graduate student in Princeton in those days, so I was actually young at that time, struggling to bring predictions of superstring theory into correspondence with the facts of nature. And this was quite an inspiring quote. And then he goes on to say, they will be led to enlarge their analytical machinery, not only to include theta functions, but mock theta functions. And you know, coming from India, Ramanujan was always an inspirational figure. So, but I never thought in those days that string theory will ever find use for mock modular forms. And so I never thought in my research I will come across them. But quite surprisingly, around 2012, I mean, around 2010 or so, we were sort of led to mock modular forms, you know, without, you know, almost against our will. And this has to do with a puzzle with black holes. This is how I got interested into mock modular forms. So, so this has to do with holography. Okay, so this is my first part of first avatar. And holography, as you know, is related to black holes. So the counting function, so as you know, the black hole has some entropy. And by Boltzmann relation, the entropy of a black hole should be the logarithm of some number, which is like is essentially some dimension of some Hilbert subspace of the quantum system that describes the black hole. So these dimensions of the Hilbert subspaces in string theory context for some special kinds of black holes, the quarter BPS black holes, for type 2 strings compactified on K3 cross T2. So if you don't know, if you have not studied this string theory from the 80s and 90s, you can just think of it as a function that is given to you. Okay, there is some counting problem. It's like counting instantons or counting, it's quite closely related to counting instantons, for example. It turns out that that counting function is related to, is given by a meromorphic Jacobi form of this form. And I have essentially introduced all the functions that appear here. B is the function that I had introduced. So B to the power m plus 1. And m here is basically the square of the magnetic charge. So the black hole has an electric charge and a magnetic charge. It's a vector actually. It's a Lorentzian vector, and you can take the square of the Lorentzian vector divided by 2, and that turns out to be an integer because it's an even integral Lorentzian lattice in which this charges take values. It's closely related to the lattice of cohomology lattice of the homology lattice of K3. So m is p squared divided by 2, and a is this function that I divide. And if you remember, a goes as z square. Yeah, I should have written this. Actually, it goes as sine square z, sine square pi z. So it goes as z square. So at z is equal to 0, it has a 0. And since a is appearing in the denominator, it has double poles in the complex z plane all over the place at all the images of z is equal to 0 by the lattice translation. So this is not the kind of function to which we can apply this theorem of ring of Jacobi forms, because those were holomorphic functions in Z. And the claim is that the quantum degeneracies of this kind of black holes, which is basically the dimension of this Hilbert subspace, if you take its logarithm, you should get the black hole entropy. The quantum degeneracies are given by Fourier coefficients of this function. However, you can immediately see this cannot be right, because quantum degeneracy should be some number that is given to you for a given system. How can it depend? Because depending, if you have a pole, then depending on the z plane, if I take my integration contour here or here, I will get a different answer for the Fourier coefficients. So this cannot be right. So what is wrong with the counting? There must be, this was a claim that was in the literature, and a very actually sort of inspired paper by Dijkgraaf, Verlinde. Without having had the complete proof, they made this conjecture. But there was something wrong with that conjecture. And what was wrong is that it could not be possibly true because there is a double pole. So what is wrong with this counting? Then there is a puzzle with instantons. If you consider the partition function, let's say of n equal to 4 four-dimensional supersymmetric gauge theory on CP2 for the gauge group SO3, the coupling constant tau, which is the theta parameter and the coupling constant, theta plus I 4 pi upon g square, you should get a function. If you take a topologically twisted, which is a topologically twisted partition function, then you can argue that the whole action is basically, so the idea of the topological twisting is that this is a theory which is supersymmetric to begin with. And then you reassign, you mix the R symmetry charges and the space, you choose a subgroup of the R symmetry group and the space-time rotation group of a four-dimensional manifold, which is SU2 cross SU2. And your R symmetry group is SU4. So you pick an appropriate subgroup and you declare that to be your new group. You look at the transformation properties of the supercharges under that group. And clearly, Q begins its life as being a spinner of the rotation group in 4 dimensions. Spin group in 4 dimensions, and it is a fundamental, it transforms in the fundamental of SU4 or in the spinner representation of SO6, which is the R symmetry group. So if you take an appropriate combination, some of the supercharges actually under that new SU2 prime, which is a combination of space-time rotation and R symmetry rotation, this becomes a scalar. And instead of Q commutator Q giving you the Hamiltonian, as one normally does, it squares to 0, a particular Q charge. And using general arguments, you can show that d by d tau bar, if you take the derivative, then it's Q of some object. And basically, the Waffa-Witten partition function computes the Q cohomological object. So you get a 0 because this is cohomologically trivial. So the expectation value is 0, naively. However, and this works very beautifully for if you, for example, take the Waffa-Witten partition function of n equal to 4 supersymmetric Yang-Mills theory, let's say SU2, on K3, then the function that you get is 1 upon eta to the 24 of tau, which is a nice modular function. And in fact, it is manifestly holomorphic. However, if you compute it for a CP2, then apparently it is not holomorphic. It turns out that there is the holomorphic partition function which receives contributions only from the instantons. It does not have the right modular properties expected from S-duality. So notice that this function is both holomorphic. So this is for K3. For K3, z of tau is 1 upon eta to the 24 of tau, which is both holomorphic and it has nice modular properties. And the nice modular properties, what is it computing actually? If you think of from a modern perspective, you can think of the gauge theory as coming by wrapping a D4 brane on the K3 or a Euclidean D3 brane on K3. And so what it is computing is the bound state of D4, D1 bound states. Or from a mathematical point of view, it's computing the elliptic genus of the instanton moduli space, because the D0 branes in the Euclidean D3 brane or D1 branes in the D4 brane are represented by instantons in the gauge theory that lives on the D4 world volume. So D1, D4 bound state corresponds to an instanton. So you can have n instantons living on the K3 surface. And what you will get is some kind of a symmetric product of K3, for example. And from those computations, you can derive that you will get this partition function. And in fact, Wafa-Witten were quite surprised by the appearance of eta to the 24 tau, because that you should remind you of the heterotic string, left moving heterotic string. And this was the first instance of the, and they conjectured that there must be something, some kind of duality. And in fact, it is related to the type 2a heterotic duality, because if you take the type 2a brane, phi brane wrapped on K3, it is the heterotic string, and by some chain of duality, it is related to D branes. So therefore, we cannot actually tolerate that this function ceases to be not modular, because modular symmetry in this case is a very fundamental S-duality symmetry of gauge theory. So again, what is wrong with duality? Something will seriously go wrong with duality if this was the case. So in particular, we would conclude that duality of supersymmetric Yang-Mills theory works for K3, but it doesn't work for CP2. And that cannot be right. So this was a puzzle actually for 20 years. And the answer to that question again involves Mach modular forms. Finally, there is a puzzle with elliptic genus. If you compute the elliptic genus of a sigma model, again, let's say sigma model on K3, then you will find the function that I wrote down before, the B function, which has nice Jacobi form properties. However, if you compute it for a non-compact manifold like a cigar, for example, which can be represented as some kind of SL2R coset, for a cigar geometry which is non-compact, you find that the elliptic genus actually is not modular. If you just keep the holomorphic part, you can get a modular object, but then it is not holomorphic. So what is wrong with conformal invariance? Because this would be something wrong with conformal invariance. Modularity, as I told you, was a consequence of the fact that the path integral was conformal invariant. So in all these three cases, the answer involves Mach modularity in a very essential way. Now, I'm going to now go a bit quickly. The poles in the counting function. So what is the resolution? The resolution is that, as I told you, this 1 upon a function had a pole like 1 upon z square. It turns out that it is a reflection of a wall crossing phenomena. Because when you are computing black holes, some quantum degeneracies of some bound states, it actually depends on where you are in the moduli space. So, and the moduli space is in fact divided in chambers, and these are walls in the moduli space. So I'm plotting here a moduli space of K3 cross T2. And whether you're here or here, on this side of the wall or that side of the wall, you actually are expected to get different bound states, number of bound states. And this is well understood in the counting, in the enumerative geometry, in the, say, the Donaldson-Thomas theory and so on. And the moduli space of the theory is divided into chambers separated by walls. And what one can show, I mean, now this is completely understood, that we can associate pole in the Z plane with a wall in the mu plane. So mu is the moduli space. And in fact, mu depends on Z in a particular way, or other way around, Z depends on mu in a particular way. That as you move around in the moduli space, when you hit a wall in the mu space, you hit a pole in the z plane, and when you cross a pole and you pick up a residue, that's when the degeneracy jumps. So this actually gives a consistent picture that in fact the degeneracy jumps as it is expected from the enumerative geometry. And however, it is inconsistent with black hole intuition, because quantum degeneracy of a black hole is expected to be a property of its horizon and not of the asymptotic moduli. So black hole really should not care what is the value of mu. A black hole is a black hole. So what happens actually from a black hole perspective is that in fact black hole horizon indeed is independent of the moduli. However, on one side of the wall you can have multi-centered black holes together with a single-centered black holes. And as you approach this wall, the multi-centered black holes sort of the distance between them keeps on increasing, and they fall out of the spectrum. And when you cross the wall, you only have single-centered black holes, and therefore the degeneracy jumps. However, the jump in the degeneracy is consistent with the fact that on one side you have multi-centered black holes, and it is not inconsistent with the fact that black hole degeneracy is completely determined by its horizon geometry. And this can be formalized, and this was actually one of the physics intuition behind this theorem of as I told you, I mean, I sort of got into this in a cafe discussion with Zagier, and I thought, okay, this is some pole, and somehow we will hack our way around. I mean, he's an expert in Jacobi forms, but he told me that no, this meromorphic Jacobi form is a completely different beast. It all goes back to Ramanujan's work. But luckily for you, my former graduate student had just solved this problem. And so that's how we got into this collaboration. And we proved this theorem that there is a, when following up on Zwegger's work, that there is a unique decomposition of this counting function. One which has no poles and is completely finite, and one which has exactly the same poles as the original function. And this is called the polar part. The polar part is given by the Appel-Lerch sum, and there is a finite part which is given by the is free of poles. And the Fourier coefficients of the finite part is what gives you the black hole degeneracies. So now this resolves the picture completely. Of course, this is not a theorem yet, because you can always decompose a function into two functions. I mean, that's not a theorem. The important part of the theorem is that each of these guys can be completed into, so the important part of the theorem is that this actually is a mock Jacobi form. So the decomposition theorem has this very nice interpretation. This polar part counts the degeneracies of the multi-centered black holes. The finite part counts the degeneracies of the single-centered black holes. And they admit a modular completion. The finite part is, the Appel-Lerch sum is constructed simply by taking some kind of an elliptic average. You have some z-square pole with some residue. So you just look at that residue and you take its average. You just take all its images by method of images. And that is called the Appel-Lerch sum. So this is the Appel-Lerch sum. And it is defined in this manner. You basically take the pole at y equal to 0, and you take its elliptic images, and that gives you the Appel-Lerch sum. And multiply by this residue, that gives you the polar part of the counting function. And then what you are left with is the finite part. And if you just count, because I'm dividing by eta to the 24, you get a mock Jacobi form of weight 2 index m. So the final statement is that the quantum degeneracies of single-centered black holes in a generic Calabi-Yau manifold are given by Fourier coefficients of not Jacobi forms, as you might have expected, but by mock Jacobi forms. And this is where Ramanujan's work comes into play. And mock Jacobi forms can be defined simply using the theta decomposition. As I told you, theta decomposition means you can just take the elliptic properties out, and you have a Jacobi form is equivalent exactly to a vector of modular forms. Instead of that, a mock Jacobi form, which is an object that we introduced in the DMZ paper, is an object whose theta decomposition gives you mock vector valued modular forms. And therefore it admits a completion. So once again, you have this XOR property that a meromorphic Jacobi form, which was counting our total degeneracies, including single-centered and multi-centered, which was holomorphic and modular, but it had poles and it was not simple. The mock Jacobi form is holomorphic, it was pole-free, but it was not modular and it was not simple. The Appel-Lerch was simple in that you could just construct it from 1 upon z square and its images. It was holomorphic, but it was not modular and it was not pole-free. And you can define now the completion of this object by taking the completions of H. If you just take the H hat here, then you will get a completion. And that completion will be modular and pole free, but it will not be holomorphic, and it's definitely not simple. And once again, you can characterize it by a holomorphic anomaly equation like that. And in this case, the holomorphic anomaly is given by the G bar of tau is a particularly simple theta function itself. So in fact, you can summarize our entire result by this very nice holomorphic anomaly equation, which is expressed entirely in terms of theta functions. Okay, and you can ask the question, given this shadow, can you construct a mock modular form which has some nice properties? It's called optimality, that whose Fourier coefficient grows as slowly as possible. And the answer is was solved famously. Sorry, what am I doing? I did something wrong. Okay, by Zagier. It turns out that the object that appears in this black hole problem was an object that was encountered by Zagier in the context of counting some fancy Hurwitz-Kronecker class numbers. Okay, you don't need to know about what they are. They are denoted by H4n. And if you just look at the holomorphic part, it is actually not modular, but you can add to it some kind of a correction term. And again, notice that you have these incomplete gamma functions appearing there, such that the net object H0 hat, it's a function of tau and tau bar, and H1 hat, they are modular. And these are the completions. And these are the objects that actually appear in the black hole counting problem. And as we will show for the CP2 problem also, exactly the same functions appear. The Zagier mock modular forms are exactly what we will appear. So now let me explain to holography and mock modularity. That what you need to understand is that if you have a black string whose near horizon geometry is ADS3, then you expect SL2Z symmetry, again, because of the fact that the solid cylinder has SL2Z as a group of global diffeomorphisms. And it would appear that somehow the holomorphic function does not have this SL2Z symmetry. So what is going on? It's related to the holomorphic elliptic genus. I think I will maybe go a bit quickly to just explain the main idea. The main idea, I want to now make a contact between this mock modularity and non-compactness. And the object that is going to help us connect these two is the gamma function. And a simple thing to consider is a Witten index. So Witten index, if you remember, is if you have a supersymmetric quantum mechanics, okay, of some manifold. So there is a particle moving on some manifold with some Hamiltonian, which is a square of a supercharge. And from the differential geometric point of view, the Hamiltonian is like the Laplacian, and Q is like the Dirac operator. So this is an object that is very closely related to the Atiyah-Singer index theorem. And this is how you can prove actually Atiyah-Singer index theorem using supersymmetric quantum mechanics. And Witten index is defined as the index partition function raised -1 to the of e to the minus beta h of this supersymmetric quantum mechanics. And again, if you have -1 to the f, for bosons it is positive, and fermions it is negative. And you can show that again bosons and fermions are related because Q acting on a boson gives you a fermion. So unless Q annihilates the states are always paired. So you can show that generically for a compact manifold, if the target manifold is compact, so if you have a supersymmetric particle moving on say K3, then this W of beta is independent of beta. So d by d beta, W of beta is 0 for a compact manifold. However, if the manifold is non-compact, as we will show you, you cannot actually make this assertion. And that's actually very similar to the holomorphic anomaly equation that I told you about. So W of beta by this argument, then you can show W of beta at beta going to 0 gives you the elliptic genus, the Atiyah-Singer index. But you can evaluate it in the other limit of beta going to infinity, or the vice versa. And then you can use the heat kernel method, beta going to 0. In the beta going to infinity, you get the index, and beta going to 0 limit, you can use the heat kernel expansion. And this is how actually Atiyah and Singer proved the Atiyah-Singer index theorem. But you can prove it using this concept, ideas of Witten, that you embed it in a supersymmetric quantum mechanics, and then you argue that in the quantum mechanics context, this quantity is beta independent. But there is a simple way to show that in a non-compact situation, because you have a continuum of states, you not only have discrete states, but you also have a continuum of states. And if you have a continuum of states, you should really talk about the bosonic density of states and the fermionic density of states. And these necessarily do not have to be equal because you're talking about a continuum. And if you define this properly, you show that actually there is a bit of a mismatch in certain contexts between the bosonic and fermionic density of states when you have a continuum of states, and they don't precisely cancel. And that lack of cancellation gives rise to a beta dependence and a kind of a temperature anomaly, if you like. D by D beta is not zero. And in a very simple problem, for example, if you consider Witten index of a supersymmetric, just a quantum supersymmetric path integrals, ordinary integral. This is an ordinary integral with 2 bosonic variables and 2 fermionic variables with this action. Then you can show that because this U and F are going over a non-compact space, if your each function does not go to 0 at infinity, but has this kind of a form, then you get the error function as for the Witten index. And the error function is nothing but the gamma function, basically, in some appropriate form. So, and because of localization, actually, many of the problems that we are encountering in this context, you can more or less all the physics is in fact contained in this simple single zero-dimensional path integral, if you like, an ordinary super integral. And the error function or the gamma functions appear for the same reason that the error function is appearing here. Okay. So the puzzle with S-duality, again, as I told you, if you had K3, you get everything looks very good. You get a holomorphic function which is modular. But if it is CP2, then sort of everything seems to break down. And once again, the answer to this question comes can be related to a non-compact theory. I will skip this topological twist. But if you think of a M-theory realization of this system, in the M-theory realization of this, you can think of it as a M5 branes wrapping. M5 branes wrapping. Yeah.
So in the previous, like the place where you show the error functions,
yes,
philosophically speaking, is the reason why the error function appears here the same as the reason why the error function appears in the Appel-Lerch sum? Not the Appel-Lerch sum, sorry, the construction, the Appel-Lerch sum in the black hole case?
No, not in the Appel-Lerch sum. It's for the same reason that it appears in the mock. The error function appears both in the Appel-Lerch sum, but also in the completion of the mock modular form, the corresponding mock modular form. So the more natural object from the path integral point of view is the mock modular form itself, not the Appel-Lerch sum. And there, in the definition of the G star, if you remember, there was a gamma function appearing, which is related to the error function.
I see.
So philosophically, it's exactly that there is a non-compactness in the field space, and you pick up contributions from the boundary, and the essence of that boundary contribution is captured essentially by this this kind of an integral, because by localization you can more or less reduce it to this kind of an integral. So I mean, it's not all the details have to be worked out, but I think that's the essence of the idea.
And just one more thing, like you're the last talk for the session, so you can take a few more minutes. You don't have to rush.
Okay, all right. Okay, thanks. I will take a few more minutes. So now if you take an M5 brane on CP2 cross sigma, let's first do it on K3 cross sigma, okay? If you take an M5 brane on K3 cross sigma, then as we know with this AGT story and so on, but okay, even before that, you can think of the M5 brane, either you take the K3 to be small or you take the sigma to be small. If you take the sigma to be small, you have a gauge theory living on K3. And its partition function, therefore, should be the same for some supersymmetric quantities. If you regard K3 to be small and consider the partition function of sigma, but on sigma, you get essentially the heterotic string theory, because M5 brane wrapped on K3 is the heterotic string. And its partition function, supersymmetric partition function, only counts the right moving ground states and the left moving excited states, which give you the eta to the 24, 1 upon eta to the 24. So this is a very simple way to understand why eta to the 24 appeared in the computation of, I mean, this would look magical to mathematicians, because why should a K3 have something to do with 24 free bosons? But as we know now that from the M theory perspective, it's very natural that depending on which limit you're taking, you get two different answers, and they have to be the same. So whether you do the calculation in gauge theory or in the sigma model, you should get the same answer, and which is 1 upon eta to the 24. So you can repeat the same story here, but the main point was that the target space was compact. Whereas here what happens is that you get a target space in the sigma model theory, which has a non-compact factor R3. So you have R3 and a compact boson, which is sort of fibered over it. And using this fact, and this content you can more or less work out explicitly. Using the fact that you have an R3 and a non-compact path integral, you can, following this path integral derivation, you can essentially derive the whole thing using the shadow explicitly. And this is the calculation that is done in my paper with, but I will just describe to you the essential features of that answer. Okay, sorry. I don't want you to run you through the calculation. I just want you to focus on the answer. If you look at the answer, the holomorphic anomaly looks like this for the CP2. It has a factor tau2 to the 3/2, eta cube tau. There is a factor of 3, and there is this anti-holomorphic sum. Now, the holomorphic sum corresponds to counting instantons. So naively, you expect that the Waffa-Witten partition function should count instantons, but somehow some anti-instantons are making their appearance here. So what is the origin of this? And we would like to understand it both from the gauge theory perspective and the sigma model perspective. And in the sigma model region, because you get R3, the eta tau to the -3 comes from the 3 left moving bosonic oscillators. Then the anti-holomorphic theta function is the contribution of the right moving moment of a compact chiral boson. There is an S1 in the game whose radius is what you require to get that theta function. And then the tau2 to the -3/2 comes from the integral over the 3 non-compact bosonic zero modes. If you remember, when you calculate a partition function of a boson, you get, for a single boson, you always get tau2 to the -1/2. So if you have 3 bosons, you get tau2 to the -3/2. So these factors are clearly something to do with the non-compact part of the theory. And the factor of 3 comes from the quantum of H flux in this story, because there is an M5 brane, there is an H flux. So this story I will not be able to explain now, but you can read it in our paper. But basically, all these 3 factors can have a very nice and natural explanation if you did the sigma model calculation using a path integral calculation, using some of the recent results of Gaiotto and Johnson-Fried. So using this Gaiotto-Johnson-Fried, you can sort of simplify this calculation, and rather than computing the error function or the gamma function, you just compute its derivative. So it simplifies the calculation. In the gauge theory calculation, the answer comes from different factors. Eta tau to the -3 comes from the Euler character of which is the contribution of point-like instantons. Anti-holomorphic theta function is the contribution of abelian anti-instantons. And tau2 to the -3/2 comes from the integral of the constant mode of some auxiliary fields. This is actually quite a complicated story, and it took us some months to sort it out. So this is all in our paper. You can look at it, it's explained in detail. But I just want to show you where the essential features come from. And the factor of 3 comes from the first Chern class of the canonical line bundle of CP2. So that which also enters naturally in this context. So we see that in these 3 different contexts, namely holography, then elliptic genera of non-compact manifolds, and gauge theories where the field space is non-compact, mock modular forms appear very naturally. Anybody who's interested in these kinds of topological questions would naturally be led to the world of mock modular forms for the same reason that modularity became important in this context. So if you are doing holography or topology or let's say duality with some non-compact aspect to the story, then you expect that mock modularity will appear wherever you expected modularity before. So I will end here actually. So this is Ramanujan's 3. I don't think Ramanujan had any idea. This is sort of very power of his kind of far-seeing ability to see mathematical patterns. that in very different physical contexts of holography, topology, and duality, some of these functions that look very exotic at the time, they appear very naturally. So I think I'll stop here.
So let's thank Atish for the fantastic talk again. Thank you, Atish.
Thanks.
Before I open the floor for questions, I just want to tell people who are leaving that we will take a picture session after this, so please stick around for a bit longer. And now you can...
Should I stop sharing?
No, please, you can continue sharing. It's only after all this. Now, anyone who has questions, please raise your hand, or please feel free to unmute yourself and ask Atish questions. Okay, there's one question on the chat. Any suggestions or problems for further research?
Well, I think, okay, if you're mathematically inclined, there are plenty of directions to pursue this in. I think generalizations to other, I mean, we sort of do a bit about it in our paper, but you can imagine generalization in different directions. I think, yeah, you have to find a problem where it is doable. I mean, for example, if you try to do a generic Calabi-Yau, the problem becomes much complicated much sooner, very quickly. But I think there has been interesting work by Piolin and Alexandrov and some others, also Greg Moore and Manshot. They have generalized, they have done n equal to 2 supersymmetric angles theory. And there are generalizations of, yeah. So I think there are interesting works to be done in the generalizations of this. Yeah, I would rather put it like that, don't be surprised if you encounter a mock modular form when you're doing something which has some non-compactness in the story. And it probably has a very natural reason why it is there. So, 10 years ago, I would have been shocked because actually when I started to work with Zagier, it was actually, I was kind of really bothered by the fact that the counting function of, it was sort of violated my holographic intuition that it should be, something should be modular, but it is not. But the modularity gets restored in a very subtle way because of some contributions coming from non-compact as parts of the field space. And now we can be, yeah, so it sort of reassures us that, okay, holography is still true. Similarly for duality, I mean, it would have looked very odd if the duality symmetry was not valid on CP2 or some manifold like that. So I think, I'm sure there will be all kinds of context. Also, meromorphic Jacobi forms appear quite naturally in many contexts. So I think there are many generalizations possible.
May I ask?
Yes. Hi, Kantara.
So, hi. So where is non-compactness in this twisted n equal to 4 super EMLs on CP2?
It's in the field space, not, it's the CP2 is, yeah, CP2 is not non-compact. It's in the field space because it's,
yeah,
because it's B2 plus is 1. Actually, simple way to think about it is that if you separate the, you can construct an SU2 gauge theory by taking 2 M5 branes. And the Coulomb branch of this M5 brane is non-compact.
Oh, I see. So there is a scalar that has a non-compact direction.
Yeah, there are actually 4 scalars. There are many scalars in there, right? You can separate it in many directions. And there is an R3 that comes, it's basically the non-compact region of the Coulomb branch.
Right. Oh, I see. Yes. And also you said there's a anti-instanton contributing.
Yes.
Why is that?
So those are the, it has to do with the fact that it is B2 plus is a...
once again. I see. Okay.
Sorry, maybe I'm saying it wrong. Yeah, okay. It's quite specific to the fact, there is a generalization to this to B2 plus equal to 1 store. Because it's basically because you have only one direction. And
I see, okay. Okay.
You have a one-dimensional lattice rather than a two-dimensional.
All right, thank you. Okay, thank you.
So any more questions?
Okay, hi. Okay, so I have a question.
Masai.
So
Yeah.
yeah, so well, so you mentioned that the mock modularity is often connected to non-compactness in some field configuration space, etc. And then so there is a tail, and which is cut off by some error function, etc. So now sometimes when there is a non-compact modular field space, etc., people try to compactify it in some way as a regularization, and then try to take the decoupling limit to go back to the original problem as a regularization. So if you follow that type, well, I don't necessarily know how to implement that in practice, but I can imagine doing that conceptually. And then it sounds like that you start with the compact moduli space as a regularized version, and that's gives rise to the modular form. So it sounds like a mock modularity can be regarded as a limit of a usual modular form. Is there some type of mathematical statement, something like that?
I'm not sure about that. I mean, see, I think there might be some topological obstruction in compactifying in these cases. So, for example, if you just take R, okay, if you just take R, your natural reaction would be to compactify on a circle, right, and then take circle going to infinity. But suppose you have a superpotential on that, which has this form, no? Suppose you have a this function superpotential which goes from minus, let's say minus lambda to plus lambda, right? Then you cannot compactify without, and the error function is actually proportional to the absolute value of lambda.
I see.
So yeah, so actually, so you have to, for example, now when you are defining a trace, right? Even simple things like defining a trace, naively actually you get something which is not a trace class. You cannot, like, you just take a free particle on R2, right? If you calculate trace e to the minus beta Hamiltonian of a free particle, it's divergent. It has the volume divergence, right? So you cannot actually define its. So how do you define it? Okay, first of all, how do you define it? So you have to use something called the Gelfand triplet to be able to make sense of non-normalizable scattering states. But even if you make sense of them rather than on a Hilbert space, right? I mean, basically, P and X in quantum mechanics, they are not normalizable wave functions. So they belong to you have to think in terms of the Gelfand triplet. But even if you think in terms of Gelfand triplet, e to the minus beta h trace will be typically divergent. It doesn't make sense. However, if you're computing trace e to the minus beta h plus minus e to the minus beta h minus in some supersymmetric context, then what can happen is that essentially the difference is localized in some region. And even though each object is not trace class, trace minus 1 to the f e to the minus beta h is actually trace class. And then you can, so you have to, I think in this context, it seems to me that you have to somehow deal with non-compactness a priori. I don't think you can compact it.
I see. Okay, thank you.
Any more questions? Atish, I have a question. At some point you said in the M theory part, it was surprising why K3 should know about 1 over eta to 24. But from the perspective of looking at, like the Hilbert scheme of K3 in the sense of Dijkgraaf-Verlinde, there it's not very surprising why K3 should know, or rather the Hilbert scheme of K3 should know about the Dedekind eta to 24, right?
But what was surprising is that they actually sort of went in the direction of conjecturing type 2 heterotic duality or M theory heterotic duality, because they said, okay, this looks like the partition function of 24 free bosons, which is like the heterotic string. Yeah, it's true that you can understand it in terms of some counting problem, like as it's a Hilbert scheme, so there is a symmetrization and there are bosons. But then the surprising thing is why is the sigma model of 24 bosons appearing in the counting problem of elliptic genus of K3 or counting of instantons and K3. And I mean, okay, so the mathematical explanation is what you're saying. If you actually do the calculation and you see the Hilbert scheme, but from a M theory perspective, now we can say that, yeah, it's kind of obvious if you believe in M theory duality, because it depends on whether K3 is small or the T2 is small. So if you think in the heterotic frame, then it would look to you like eta to the 24 is coming from the. Yeah, so I think it sort of gives the, it gives an evidence for, depending on how you look at it, it gives you evidence for M theory duality, or if you believe in M theory duality, then you can sort of predict these things.
Probably one more question. Would you perhaps be willing to very succinctly tell us what you're doing with Diksha and Francesca?
I'm trying to derive this elliptic genus, the shadow from first principles in ADS3 holography.
I see.
And that was an unsolved problem, which I think, okay, we have some partial progress in that. I think we are close to, but we are not completely done yet.
I see.
Yeah, so I think DMC gives you an answer, but we would like to understand it from the ADS3 holographic perspective.
That's interesting. Yeah, are there any more questions for Atish?
Yeah, it would have been really nice. I remember my last visit to, I would have missed wonderful dinners in Tokyo and sushi, and maybe next time it will be in person. It will be good to visit.
Yeah, you should come back.
Yes. I was looking forward to it, but okay, it didn't happen.
Okay. So let's thank Atish again for the fantastic talk.
Thanks. Thanks, Abhiram. Thanks, Kantaro.
I would like to, Atish, if it's okay, do you mind stopping your screen share?
Yeah, yes.
And if everyone is okay with that, if you're like an appropriate surrounding and whatever, if you're okay with turning your camera on, please do so, and we will have a little workshop picture. We should have done this yesterday. We kind of forgot about it.